So now I get the pleasure of turning over the job of introducing speakers and keeping them on time to Dave DeBoer, who has done so much to organize this meeting and for whom we are very grateful and thankful. So Dave, it's yours now.
Great. All right. Thanks, Jill. Thanks for keeping us on time. All fascinating talks. Time's gone so quickly. One of the things you'll notice is that we didn't schedule in explicit breaks, but that is one of the joys and advantages, I guess, of Zoom, is that people can do so at their convenience. For the last session this afternoon, we're going to look at exploring life on some of our favorite planets in the solar system, Mars and Venus, which is kind of gay new life in the life regime, and then look at ways to detect both agnostic biosignatures and technosignatures. So to start off, we have Dr. Tim Goudge, who's an assistant professor at the Department of Geological Sciences at UT Austin, and a CFAR Azrieli Global Scholar with degrees from Queen's University in Brown. Tim's research focuses on the use of remote sensing data to study the record of surface processes on the Mars, Earth, and other planetary bodies. And today, he'll be speaking about exploring habitability on Mars. Thanks, Tim. Your slides look great, and take off.
Great. Well, thanks for the kind introduction, and thanks everyone for tuning in. I'm excited to talk to you today about now sort of zooming in on some of the records of habitability on planets within our solar system that actually, as you'll see throughout the talk, has been very nicely set up by what both Jim and Francis discussed to us over the last hour. So for the next 40 or so minutes, we're going to be thinking exclusively about Mars. So I thought and sort of the geologic record of Mars. So what does the surface environment look like, both in the modern and mostly in the past? And so I think it's useful to start, what does the surface environment of Mars look like today, right? And so when we conjure an image of Mars in our head, or at least when I conjure an image of Mars in my head, this is what I sort of envision, right? This is an image from the MSL Curiosity rover, taken of this sort of red, dusty, seemingly harsh landscape, right? And this is sort of modern Mars. And indeed, modern Mars's environment is one that is fairly harsh in terms of thinking about conditions under which life tends to thrive. And so two of the ways we might characterize that are surface temperature and amount of water available. And so Mars is both very cold environment with average surface temperatures around -60 degrees C. Certainly this is quite spatially variable as well as temporally variable. So at certain times of year, certain times of day, and certain places of the planet, it does get above 0 degrees C, but on average, Mars is a very cold surface environment. It's also a very dry environment. And so one way we might try and quantify that is by asking how much water is in the atmosphere. So Mars has a thinner atmosphere than Earth, about 1% the atmospheric pressure, which is predominantly CO2. But in that atmosphere, there's not very much water. And so if you take the atmospheric column above any given spot on the planet and collapse it down and sort of measure how much water you would get out of that entire atmospheric column, that gives you the precipitable amount of water, how much water could precipitate out of that atmosphere. And on Mars, that value is sort of around, would be measured in microns, which is sort of order thickness of human hairs. On Earth, it's obviously quite variable spatially and temporally, but it sits more around centimeters. So a couple orders of magnitude difference between the amount of water in Earth's atmosphere and Mars's atmosphere. But as we've been hearing about over the last hour, and as I'm sure many people on this conference are familiar with, right? Mars has actually quite an abundance of evidence, geologic evidence for water early in its history. And I'm going to define what I mean by early. When I say early Mars or ancient Mars, I'm going to define what I mean by that on the next slide. But what I'm showing here is an image of a river valley. So it's this sort of sinuous feature here that is, for scale, right? It's over 500 kilometers long. It's a couple kilometers wide, and It's over 800 meters deep and can reach kilometers deep in some locations. And so scale, I'm going to be showing you a lot of images from orbital satellites of the surface of Mars. And scale can be a little challenging, I think, to get from some of these images. And so one of the things I want to emphasize is, okay, scale is really important when we're thinking about these images. So when we look at this image of a river valley, we should not be thinking about, the Colorado River sitting at the base of the Grand Canyon, right? We should be thinking about the Grand Canyon itself, this large feature carved into the landscape over long periods of time by the action of this river, which moves water and moves sediment across the landscape. And so, over the last sort of 50 years, our understanding of what the hydroclimate and hydrology of early Mars looked like has been really rapidly advanced by, a large number of orbital and surface missions. And so if we take all of that evidence and put it together into a sort of very schematic diagram of what Mars's hydrologic evolution looked like, we can come up with a plot that looks like this, where the present is on the right, so time is on the x-axis here. Modern Mars is on the right, and going back in time, there's this big gap here. And so we have now 3.5, and 4 billion years. And on the y-axis is sort of a qualitative sense of how much water is around and how much water is around at the surface, I should say, and how much geologic work that water is doing. How much is it reshaping the landscape? And the key is that, this time period right around 3.6, 3.7, 3.8 billion years ago, at this transition between two major eras on Mars, the Noachian and the Hesperian, this is when we think there was most water activity, when water activity was most abundant on the surface, right? And as we've heard about, right, this time period is really, really quite important because this time period when Mars had what we think is its most abundant liquid water is sort of right around the time when we find the first both geochemical signs of life as well as the first preserved fossil evidence of life on Earth, right? So sort of 3.5 billion year time frame. And so this raises two key questions when we think about ancient water and the search for life on Mars. The first is that, well, could early Mars have been an environment that would have supported life as we know it? Right? This is the question of, was early Mars a habitable environment? And this is different from the question of, was it an inhabited environment, right? Which, was it an inhabited environment is the second one, which is, did life ever exist on Mars? And so these are sort of some key questions when we think about the search for life on Mars. And planetary scientists and planetary geologists such as myself, we work to constrain these questions by looking at the Martian rock record, looking at its geology to try and put some constraints on our understanding of these sort of two really big scale questions for early Mars's potential for life. And we do this from both orbit and in situ, so with rovers, which we've heard a little bit about. For most of the talk today, I'm going to be talking to you about a habitability related question that we've been working on in my group using mostly orbital data. And that's going to be a question surrounding timing of water. How long was water available? Which I think Francis beautifully set up the importance of this question for thinking about whether life on Mars might have been able to evolve, right? We need to understand the time scale of water reservoirs. And so I'm going to present to you some work that we've been doing on that. And then I'll end by talking about the search for ancient life on Mars, focused on some ongoing work with rovers that Jim also touched on. So for my work, one of the things that I focus on is understanding Paleolake basins and studying Paleolake basins. And so an example of this is shown, an image on the right. Here's a 10-kilometer scale bar. these have been one of our key records of ancient surface water that have been really well studied, both from orbit and in situ. So they've been host to several of our Mars rovers. And they're such enticing locations to study for geologists such as myself, because they're directly linked to surface runoff in the climate, right? So here, this is an impact crater here. It has one of these river valleys that flows into it, would have fed water into this basin. In this case, it also has a river valley that drains out, so water would have sort of spilled in and flowed out of this lake. And so there's sort of this direct link to surface hydrology. Another really exciting thing about lake basins, known from study of lakes and ancient lake deposits on Earth, is that they serve as very effective traps for sediment. And effective traps for sediment preserve paleo-environmental information. As sediment is deposited within a basin, it records surface environmental conditions. And so if we can look at records of sedimentary deposits, we can try and back out that paleo-environmental information. And so there is at the mouth of this particular inlet here, there is a fan-shaped deposit of sediment that would have recorded what the Martian landscape was like and what the Martian surface environment was like when this sediment was formed within this lake. And I showed one example of a lake, but these features are common across the Martian surface. So I'm showing a global map of Mars here. This is shown with topography using a color bar that I'm going to be showing a number of times throughout the talk, where high elevations are in white and yellow, and low elevations are in sort of various shades of blue. And so we can see, all of these dots represent individual Paleolake basins, and they're confined mostly to the older southern hemisphere of Mars, the ancient Martian highlands. And you might notice that there's both black and white dots, and of these 250 Paleolake basins that have been identified, we commonly split them up based on their hydrology. And so the two hydrologic classes we have are shown, examples are shown here. So one class is what we would call open basins or open basin lakes. And these are those, again, they're going to be commonly contained within impact craters, but these are ones where water has flown into the crater as well as water flowing out. And this is an example of Jezero crater, which is the exploration site for the Mars 2020 rover. And this geometric configuration tells us that water must have actually ponded within the basin. So we know that this basin completely filled up until it was able to breach its confining topography, right? This outlet valley didn't originally exist when this basin started filling with water, but eventually it filled up with enough water that it spilled over its edges and carved this outlet canyon as water poured out of the lake. And we can contrast that with closed basins or hydrologically closed basin lakes. And these are those where we only see valleys flowing into the basin, right? So only water flowing in. There's no sign that enough water filled the basin interior to actually cause it to overflow and breach, right? So we don't actually know how much water filled these basins. All we can say is that, okay, not enough filled, or not enough water flowed in to completely fill it to where it might have overtopped, because we don't see any record of that. So these are our two hydrologic classes of basins. And in some instances, we actually see them occurring, co-occurring within the same connected system in what we would call embedded systems. And these are really interesting geologic features, and I'm hopefully going to try and convince you that they're really important for reading Mars's climate record. And these are ones where we have an inlet valley flowing into an open basin lake that we know must have filled up, breached to form an outlet, and then downstream, that outlet actually flows in to a closed basin lake. So the outlet downstream becomes the inlet for a closed basin lake. And this hydrologic configuration is really, really useful because we sort of now have two end member constraints. We know that this basin did fill up with water, and this one did not fill up with water. The closed basin lake never received enough surface water over a long enough time to fill up with water in its interior, whereas the open basin lake must have. And so we can use this hydrologic configuration to constrain this question I mentioned at the start, which is how long was surface water sort of roughly continuously available? So that question that Francis set up is, a really important one we want to understand for thinking about whether life on Mars could have evolved. And so I'm going to show you work to try and use this configuration to address this question. And really, this work is done was led by Gaia Stuckey-DeQuay, who was a postdoc working in my group for the last couple of years. She's since moved on and will be starting a faculty position at MIT, but she was the one to really, understand the significance of these systems and push them forward to try and work on constraints of the Martian paleoclimate. So I'm going to walk you through a sort of schematic of how we've tried to use this hydrologic configuration to constrain time, right? So time is going to be our big question. How long were these lakes receiving water? And so what I'm plotting here is, it's going to be schematic, sort of like conceptual diagram to explain our approach. On the x-axis is time, unitless for now, but I'll show you our approach to how we try and get actual values on here. And then on the y-axis is lake volume. I'm going to show two curves, which are sort of the filling curves of the two lakes within a given embedded system. So closed lakes in red and open lakes in blue. So if we start from time 0, where both lakes are completely empty and then water starts flowing in, the lake volume is going to start to increase at a rate proportional to the catchment size of that lake and the precipitation on that catchment, as well as losses both to groundwater and evaporative losses, which are sort of worked in here. All right, the bigger the catchment or the more precipitation a basin sees, the steeper this slope will be. So these start filling at some rate proportional to their catchment and the amount of surface runoff they can generate, which is given by the precipitation on that catchment, either rainfall or snowmelt. At some point, right, we know this open lake filled completely. And so when the open basin fills to a point where it reaches the maximum constraining volume, it will breach. And as it breaches, it actually carves this outlet canyon. So I'm showing a schematic diagram on the right. This is this through-going system here. And if we zoom in on the breach, the original confining topography might have been up here. And then as you erode the outlet, you drop the water level down. We know from a bunch of other work that I've been leading with my group, as well as others, have showed that these breaches occur very, very rapidly. And so probably what happens is the volume of this lake, the open basin lake, drops incredibly rapidly, right? So rapid in terms of geologic time. So we would think on order days, weeks, or perhaps months. So essentially instantaneous geologically. And all of that water is going to be transferred downstream to the closed basin lake that the outlet ultimately feeds. So sort of in this step function, the closed basin lake volume increases and the open basin lake volume decreases. Once breached, the open basin lake will hold a stable lake level as the outlet is able to have water flow out it. And so we can hold a stable lake level in that open basin lake. Whereas now, the closed basin lake is going to increase its volume at a steeper or faster rate because it is now receiving water not from its own catchment, but also from the catchment of the open basin lake. So all of the water from precipitation that's making it into the open basin lake is leaving through the outlet, right? It doesn't lead to an increase in the volume of the open basin lake, which is being held at a steady level. And so instead it goes into the closed basin lake. And how much this rate increases, we sort of don't know where along this curve the system must shut down. We can only say it never gets to this volume. This is a volume we can measure to say this is the maximum capacity that this lake could hold, this closed basin lake could hold before it too would have breached, for which we don't see any evidence. So we know that this volume never could have been reached. And so what we end up with is sort of a bounded time scale, or what we've called a permitted time scale, right? So on this, for now, unitless time axis, we know that we have to fall in this range. We have to have received enough precipitation off of the catchment for the open basin lake to breach. So we have to be on this half or on this side of this time scale. We also know that the closed basin lake never did breach. And so we have to be on this side of this part of the permitted time scale. So we have this sort of range of time scales or time spans that would be permitted for any given embedded system to constrain the geometry that a closed or an open basin lake feeds into a downstream closed basin lake. So to get this into absolute times, we need to have values for all these things, right? So the geometric values are actually fairly straightforward to get from modern orbital data. So the volume, the maximum constraining volume of the open basin lake, the maximum constraining volume of the closed basin lake, we can measure these from surface topography. We can use the surface topography also to delineate catchment areas where water would flow into the basin, so we can get at the two catchment sizes. So the last thing we're left with is understanding precipitation rates, as well as evaporative losses, sort of net precipitation or net surface runoff rates. So this is the last thing we're sort of left with to try and figure out a way to constrain to actually get a hard value for this permitted time span. And so our approach for doing this has been to use outputs of precipitation, both rainfall and snowmelt that have been corrected for evaporative losses, from numerical climate models from the early Mars environment. And so I'm showing here an example from Robin Wordsworth across sort of a central swath of Mars on the top here, and then a zoomed in portion here. And the color bar shows precipitation rate, meters per year, varying over several orders of magnitude. And we can take these climate outputs and average them across the watershed to get some average value of runoff, average value of precipitation, which we can then feed in. And we can do this spatially resolved. So for each embedded system, we can look at what the climate proxy is, or the climate data suggests for that region of Mars. And so we end up getting a precipitation rate that varies between these embedded systems, for which we have not quite a dozen. And so we now have all the values we need to actually calculate a time span. But as anybody who has participated in climate modeling studies or is familiar with that field, right, there's a huge range of uncertainties in trying to reconstruct the climate of Mars 3.7 billion years ago, right? It's not that surprising a statement to make that there's large uncertainties in that. Those uncertainties range from understanding the appropriate physics to put into the models to understanding the appropriate boundary conditions under which those models are operating. And so to try and keep our results as generalized as possible, we used a suite of model outputs. So we got outputs of precipitation from 14 different climate models that vary multiple parameters, vary the physics. So they vary atmospheric pressure, the obliquity or axial tilt of the planet, what type of precipitation there is it rainfall or snowmelt, and what's the total water inventory, all things that might be important parameters for reconstructing the Martian climate. And so here's a suite of 4 different climate models, all shown for the same location. The citation is shown in the top right, but you don't need to study the details of this other than to say, okay, well, there's quite a lot of spatial variation within a given model. There's also a lot of model to model variability, right? So we're encompassing a range of several orders of magnitude in terms of how much precipitation might be expected across these watersheds. And so we take our climate model output suites and we plug it into our embedded systems, and we ask the question for a given time scale, how many embedded systems are satisfied? So this is sort of what the output looks like for a given absolute time scale. So we're just going to talk through an example of, say, for 1,000 years. Say you have continuous runoff for 1,000 years. How does that satisfy the systems, the embedded systems we have for a range of different model runoff rates? And so the dots here are showing, what fraction of embedded systems are satisfied. And the size and color of the dot says how many climate models fall within that range. So for this top point here, we're satisfying like 70% of the embedded systems, and about 4 of our 14 fall at a range of satisfying about 70% of the embedded systems. And so we can do this, we can calculate the statistics on this, right? So here we have a median and an interquartile range. And we can now do this at a range of timescales. And what we get is a plot that looks like this. And so, if you were to satisfy all embedded systems, you would be up here for an 1,000-year duration of runoff episode, or a duration of a runoff episode. So there are a couple points I want to make from this plot. The first is that if you have runoff durations less than about 100 years, or more than about 100,000 years, you can't satisfy very many of these embedded systems, if any at all, regardless of what your climate model is. And the reason for that, right, is very short runoff episodes don't provide enough runoff to fill open basin lakes, whereas very long runoff episodes always fill the closed basin lakes. And so instead, our sort of sweet spot of where you can satisfy the most systems is sort of between 1,000 and 10,000 years, right? So 10 to the 3 to 10 to the 4 years. One thing I also think is really interesting from these results is that never do we get anywhere close to satisfying all of the systems. We never even come close to approaching 1, right? Our highest medians are satisfying like 60% of the embedded systems that we've identified. I think that partially has to do with, telling us that, okay, probably our understanding of the early Mars climate and our ability to numerically model it is not perfect. But I also think this is actually telling us something real about the Martian surface and real about how we should think about these durations, right? What does this duration of 10 to the 3 to 10 to the 4 years mean? Is that like the total amount of time water is available on early Mars? And I would argue, no, it's not at all the total amount of time water is available. Rather, if we think about an oscillating climate, so something that Francis also brought up, this idea that Mars might go through periods where water is available at the surface and periods where it's not. So you might have a runoff production versus time curve that looks like this. And so what we're looking at is sort of like the longest or one of the longest for that region runoff episodes. So there might be many, many previous runoff episodes, and there might be many subsequent runoff episodes, but all of which fall in the sort of hydrologic constraints we can see from the geology. And I think, in fact, there's lots of other evidence to suggest that there are numerous runoff episodes that occur throughout the sort of few 100 million years in which Mars experienced surface water. So you might have numerous episodes, each of which is maybe 1,000 or a few tens of thousands of years in length. And so this study I've presented, and I think orbital studies in general are really useful because they sort of give us a framework in which to consider the global picture of water availability on Mars. When we start trying to think about what that actually means for whether life did evolve in a given location and whether we might be able to find evidence of that life in the rock record, I think we need to really start thinking on the individual basin scale. And I do think that lake basins are still a fantastic place to look for this type of evidence, but we probably need to look at individual basins. And to do this best and to do it with the highest fidelity, we really need in situ observations from rovers. I think Francis mentioned this before, but rovers, we think of like Mars field geologists, right? Really going and interrogating outcrop at detailed levels. So this is a family portrait of rovers from Mars rovers from NASA, and I'm going to be talking to you about two rovers very briefly that have the same chassis, which is shown on the right here, the Mars Science Laboratory and Mars 2020. We heard a little bit about this from Jim about an hour ago, and I'm going to talk a little bit more about it sort of in the context of thinking of them as lake systems. And so since 2012, MSL has been exploring Gale Crater, which is shown on the right here. Here's Gale Crater. It is actually one of these closed basin lakes, so it has a valley system flowing into it, but no valley system leaving it. Observations of sedimentary deposits within Gale Crater have indicated, as Jim said, that it was a habitable environment, right? So it had all of the necessary geochemical elements for life. And then what Jim said, and I'm going to echo, what I think is one of the most remarkable identification or discoveries from the Mars Science Laboratory is that it's identified complex organic molecules that have been preserved in sedimentary rock on Mars for over 3 billion years. All right, this is a remarkable observation. And this is showing a drill core from which the tailings were fed into the SAM instrument and through a GCMS instrument that gives signatures of these complex organic molecules, although we aren't yet able to distinguish whether these are abiotic or biotic. But it still shows us remarkably that from a preservation standpoint, biotic organics can be identified. They can be preserved for billions of years in rocks on Mars that can be identified with instruments that we can send on a rover to explore on Mars. It's just quite mind-boggling in terms of planetary exploration and engineering, let alone from a science standpoint. And so I think this puts the next question forward is, well, okay, biotic organics, if they were around, should also, it stands to reason that they could be preserved in the rock record. And so the question is, did they ever exist, right? Did Mars form its own biologic material, and is that biotic matter preserved in the rock record? And so this is where Mars 2020 steps in, which is explicitly searching for potential past life and potential biosignatures. And this is an image captured on February 18th of this year as the Mars 2020 rover was being lowered to the surface by a sky crane. Another remarkable engineering feat, and I think just kind of an eye-opening view of planetary exploration, right? Especially when you think the scale of this is sort of like a small car. And so Mars 2020 landed and is presently exploring within Jezero crater, which is a 45-kilometer diameter crater. It's an open basin lake, so it has valleys that flow into it and a valley that flows out of it. Here's where Perseverance is right now. This lake was about the size of Lake Tahoe or Lake Winnipeg that was active during this sort of peak period of early Mars water activity. And one of the sort of key leading points for why this site was chosen, as Jim alluded to, is at the mouth of the Western Inlet Valley here is this beautiful fan-shaped sedimentary deposit interpreted as a river delta. So as rivers flow into a standing body of water, they lose momentum in their ability to carry sediment that they're moving downstream. They deposit that sediment in the near shore and start forming new land. And this is the preserved remnant, preserved outcrop of a delta deposit, right? Some of the famous examples we have on Earth, the Mississippi River Delta, the Nile River Delta, these large regions of sediment accumulation at a shoreline. And so from orbit, we put forth the hypothesis. A number of workers have suggested that this was a delta. And indeed, initial results from the Perseverance rover have confirmed this hypothesis from observations of this small outcrop here. And I'm really harping on this idea that it's a delta and that's a big deal, and it's a very exciting place to explore. And I think the reason for that has to do with the search for past life, because our understanding of the physics of sediment transport tells us that on Earth, river deltas can collect and concentrate organic matter in very specific locations. So I'm showing an example of the Mississippi River Delta here, and here's the Wax Lake outlet and Atchafalaya deltas over here. But when this river's in flood, it's carrying a lot of sediment. And that sediment, much of it is very fine-grained, and that fine-grained sediment is typically associated both in terms of grain size and electrostatically with organic matter. That organic matter travels out into the basin in plumes of sediment, and that ends up concentrating the organic matter in very specific intervals. And so that's being shown here. This is a plot of distance offshore on the x-axis versus organic carbon on the y-axis. This is not from a modern delta. This is actually from Jurassic age deposits from the North Sea. And what we can see is that the organic matter concentration exponentially increases as we go towards the offshore. This is organic matter carried by these sediment plumes. And we understand in quite a lot of detail from our understanding of the architecture of sedimentary deposits of deltas on Earth, where these should end up and where the rover should explore for any potential concentrated organic matter. And so much like the Mississippi River collects water and sediment from a huge chunk of continental North America, Jezero crater also collected water and sediment and potentially organic matter from a very large area as well, right? So its watershed area, the area in which water and sediment and any existing organic matter drained into the lake, is over 30,000 square kilometers. So a significant fraction of the land surface all pouring into this lake and collecting organic matter in what we would interpret to be the lowest, stratigraphically lowest, most offshore bases. And so as Jim mentioned, right, one of the, again, remarkable and exciting aspects of Mars 2020 is that it's going to collect samples to to bring back to Earth. So these sort of pencil-sized samples that will be brought back to Earth in a series of missions, the architecture of which Francis showed us a slide on as well. And sample collection's already underway, which is remarkable, right? For a rover that landed, 9 months ago, it's already collecting samples. Here's an example of the arm collecting a sample. It's up against these rocks here. Here's the coring bit, and this is the sample right here. This was collected last week. This sample might at some point make it back to Earth for analysis by all sorts of laboratory geoscientists on Earth. Really, really remarkable. So much to be, much future excitement from this mission, sure, which is still in its early days, even though it's collecting samples and delivering great science. And so with that, I'll end on my take-home points here, just a few key take-home points. And I think in the interest of time, I'll end on this slide, and y'all in the audience can read them yourselves, but I'll be happy if there's time to take any questions. So thanks for listening.
Great. Thanks very much, Tan. It's fascinating. It's just kind of wonderful to see Mars portrayed as such a dynamic surface, right? We tend to not think of it in that way, but that picture is emerging. Your last talk about delta leads into one of the questions in Q&A from Robin Catchpole, is that how do the models square with the amount of material shifted into the deltas? For example, could you shift all of that material in one event, or is it gradual over time?
Yeah, that's a phenomenal question. There's not enough water to do it in one event. And so when I sort of glossed over all of the things that might lead us to this type of view of the early Mars hydrology, where we have, multiple cycles of surface water and surface runoff. If you look at the volume of sediment, either deposited in deltas, or it's actually much easier to preserve over long periods of time, erosional signatures. So if you look at the eroded volume from the valleys that feed in, you cannot move that sediment in one of these episodes. And so that, I think, really tells you need multiple of these episodes to move sediment around on the landscape, but you only breach in one of these episodes. So it's the sort of longest one that constrains that sort of breaching time scale. But there must have been other episodes that move sediment around as well.
Great, thanks. We're almost out of time, but I'd like to, take the prerogative for one quick question. One of the things I've
Sure.
always wondered about is the water availability on the surface. Maybe I don't have even a basic picture. Is what's driving it mostly solar insolation on a carbon atmosphere? What role does volcanism play? I mean, what would drive these periodic, spates of the ability to have runoff?
Yeah, that's another really interesting question, and I think pushes into the realm of trying to understand the planetary scale geodynamics, as well as how that's coupled, like how the solid Earth couples with the atmosphere. So a couple of the examples you gave I think are really good ones, right? Major changes in obliquity, shifts of less than a degree in Earth's axial tilt lead to glacial interglacial cycles. Earth's axial tilt is stabilized by our moon, which sort of gravitationally bounds us to a well of stable axial tilt. Mars has two very small moons that have little effect on its ability to tilt. And so it's likely there were really dramatic shifts in Mars's obliquity. And I think that all of the climate models we've seen certainly tell us that has a major impact on water availability. So that's something that could give periodic changes in surface water availability. Volcanism is another one, inputting lots of greenhouse gases into the atmosphere, which lead to warming, which then maybe through a buffering cycle, get those greenhouse gases out of the atmosphere into surface deposits. Cycles like that certainly is another one that I think is really interesting.